Okay, so this is the video for the trilogy, the combined science paper. I'll do it question by question. First question that I gave you was about electrolysis, an important topic, comes up very often, tricky topic, so you may have found the first question tough, but we'll see how we get on. So in this question, you've got potassium sulfate solution. So we've got potassium sulfate dissolved in water, and we've got hydrogen and oxygen being produced. So we're expected to know that you get hydrogen and oxygen being produced, and if you don't know the reasons why, that's worth spending some time on as you're revising, because that is a difficult topic. But for now, I'll just go through the questions in the paper. So potassium sulfate contains K plus and SO4 2 minus ions, sulfate ions and potassium ions. You have to work out the formula. So for every sulfate, so compounds, ionic compounds always end up being zero charge. So we must have 2 potassium ions for every 1 sulfate ion. So it's K2 SO4, 2 pluses and 1 2 minus. It's K2 SO4 for your first answer there. What are the volumes of gas collected? So this question was done pretty well. All you've got to do is read off the measuring cylinders. The volume of hydrogen was 30 and oxygen 15. Pretty much a hopefully pretty straightforward question there. Most of you got that without any bother. Right. So the student suggested the volumes would be in the same ratio as hydrogen atoms to oxygen atoms in a water molecule. So in what way does the volume collected in the experiment support the student's hypothesis? So first of all, you've just got to state the obvious really, which is in water, H2O, the ratio of hydrogen to oxygen is 2 to 1, and that matches what you've got up here, doesn't it? Which is a 2 to 1 ratio. So the first thing is to say that it's a 2 to 1 ratio in water, and then for the second point, make it clear in some way that this matches the ratio, ratio of gases collected. This idea that it matches that ratio. Okay, and that's it. So the pause there was because I was reading an alternative answer. I think is if you got this wrong, the volume's up here wrong, you then have to say the student would not be right because the volumes don't match what was given, what the ratio is in water. That's the alternative answer, but that wasn't needed too often. Right, so let's skip on. So question 2.4, if you do the experiment 4 times, you get 4 different values, 8, 9, 10 and 11. The mean was worked out for you as 9 centimeters cubed, which is 6 add 9 add 10 and 11 divided by 3. But that was done for you. So and the answers here is 9 centimeters cubed, right? So what about the uncertainty? Now the biggest difference from the value 9 in any of the readings is 3 centimeters cubed. Right? So the biggest difference from 6 to 9 is 3, 9 to 10 is 1, 9 to 11 is 2. But that's the biggest difference, so that's why this one is the biggest uncertainty. So that is the uncertainty. All the other values fall within 6 to 12, in other words. Right, so that's what that's saying there. Question 2.5. Potassium sulfate is has 0.86 grams dissolved in 25 centimeters cubed of water. So what mass would you need to make 1 decimeter cubed or 1 litre of solvent? So you can do this a couple of different ways. So 1 dm cubed of solution is the same as 1,000 centimeters cubed. You expected to know that. So how many times does 25 go into 1,000? Well, the answer is 40. So 40 times. So 25 goes into 1,040 times, so you can do 40 times 0.86, and that way works quite nicely and gives you 34.4 grams, or grams per decimeter cubed if you like. you can do it using the sort of concentration calculation that you've learned. So concentration in grams per decimeter cubed is equal to the mass divided by the volume, and therefore what you can say is that the mass, which is 0.86 grams, divided by the volume, we've now got to, if we're going to do it this way, we've got to convert to decimeters cubed straight away, so it's 0.025, and that also comes to 34.4 grams per decimeter cubed, if you like, which is what it's asking us to do. How many grams in a decimeter cubed? So the answer there is 34.4 grams. Personally, I quite like this way of doing it. I think it's easier, but it doesn't matter. It's up to you. You get the same answer either way. Right, let's skip on and do question 4 as well. So the group 7 elements are simply known as the halogens. That's just a fact you have to know as part of the periodic table topic about elements in group 1, the alkaline metals, elements in group 7, the halogens, and the noble gases, which are group 0, group 8. You're expected to know that these are the halogens, and that includes F2, Cl2, Br2, and I2. Okay, don't really need to know much about fluorine. And we expected to know things like the order of reactivity increases up the group, and the melting points and boiling points increase down the group, right? But why do they react in the same way? Well, elements in any group have the same number of electrons in the outermost shell. So they have 7 in the outermost shell, so all have 7 electrons in outer shell. Gets the mark. You could all simply say it has 7 outer electrons, or the same number of outer electrons, or they all need 1 electron to complete their outer shell. All of that is okay. All right. Now, I always find it's interesting how tricky people find these diagrams, so it's worth just talking you through it. What you've got here is one of those kind of stick diagrams where every one of these kind of grey blobs represents an oxygen atom, as set out here. So there's 1, 2, 3, 4, 5, 6, 7 of those all joined together. The lines in between are representing the bonds. And so there's 7 chlorines, 7 times chlorine, and there are, I'm sorry, they're oxygens, aren't they? What am I doing? 7 times oxygens, and there are 1, 2 times chlorines. So you can write the equation as Cl, or the formula of the substance is Cl2O7. Okay, so that's the way we write that. If you wrote O7Cl2, you should have probably got the mark as well. Right, so you've got some melting points of the group 7 elements here. As I mentioned, we expected to know melting points and boiling points increase as you go down the group. So the melting point of fluorine is minus 220. You've simply got to put that on the graph, and there was very few problems with this one. First thing to do really is to make sure you've labelled the axes properly. Minus 200, minus 250. To complete the scale, we've done that, so that's 1 mark. You had to get it all the way down to 250, I think, for the mark. You did, yes. And then you plot the bar at 220, so each gap is 10. So the line would go here. I'm going to try and make it be nice and neat and match up with the other ones in terms of its width. And it should go all the way up to the line here. There we go. That'll do. Job done. And it was allowing a tolerance of half a small square, but something like that will do. The key thing is you get it right at that position there, which is minus 220. 2 marks for that. The melting point, though, the trend is they have higher melting points as they go down the group, and that matches the graph, doesn't it? Melting points increase that way on the graph you've just seen. So what's going on there? Let's just think about this for a second. Let's spend a little moment on this one. So the substances we're talking about are fluorine. Don't forget they're all diatomic. Chlorine, bromine, iodine. Okay, it would apply to astatine as well, which is the next one down. Right. These are all non-metals. So each substance is made only of non-metals, so they're simple covalent. Now if you're talking about simple covalent, that means they are molecules. Okay, that's what the word molecule means. It's referring to simple covalent. So you expected to know that simple covalent is just non-metal atoms with the sharing of pairs of electrons, and you've got molecules. So this is when you've got weak forces between molecules. So when you boil them, the bonds don't break. So I'm just going to draw a quick example of what I mean. So there's a fluorine molecule like that, another fluorine molecule, and another fluorine molecule. Those bonds are strong, but there are weak forces between each molecule of fluorine, which we call intermolecular forces, and that's what we have to say here. So there's weak intermolecular forces down between molecules. But what you have to say is that the intermolecular forces get bigger as you go down the group. So for the first mark then, intermolecular forces get stronger down the group, and there's nothing there that you couldn't have worked out from the question. Okay, really, so the intermolecular forces get stronger down the group. We know that because the melting points increase. And don't forget the bonds don't break, it's just these forces. But to get the marks, the other marks here, we have to really explain why the intermolecular forces get bigger down the group. And essentially it's all to do with the size of the molecule. So intermolecular forces is all to do with the size of the molecule, the number of electrons they've got. So larger molecules down the group. Okay, this is a harder question, so I didn't think many people here would get 3 marks. This is a tough question, but you know this also from the fuels topic. So as you get longer chain hydrocarbons, the boiling points also increase for exactly the same reason. The bigger the molecules, the more contact points they've got, the more electrons they have, the bigger the intermolecular forces. You get the 3rd mark, by the way, for saying the melting point increases. Down the group. So it's just stating the fact from the previous page. So what's the state symbol for bromine at -50? Well, we need to look at our graph. For that, we look at bromine, and its melting point is like -5 or something. So anything below -5, it would be a solid. So at -50 is a solid. So that's there. So you didn't need to know that. You can work that out just from looking at the graph you've been given. 4.7. Evaporation and boiling occur at the surface of bromine at its boiling point. Name one more process happening at its boiling point. Right, so at its boiling point, the boiling point, I'm going to take a step away from this and take a think about ice for a second. So if you take water and cool it down to 0, that water starts to freeze. But if you take ice, very cold ice, and warm it up to 0, it starts to melt. So the melting point and the freezing point are the same thing. Okay, so ice would start to melt at 0, water would start to freeze at 0. So you've got both processes going on at more or less like an equilibrium. The same sort of thing happens at boiling points. So at the boiling point, at exactly the boiling point, not above it, boiling would occur, but also the opposite process would occur, which is condensation. Condensation. Anything above its boiling point, there'd be much less condensation and much more boiling. I'm going to stop there.